sporting events. So, whether you're playing racquetball or baseball or tennis, a ball that goes flying up seems to always come down. But is that always the case? Is it always true that what goes up must come back down? So many questions, so much to explore. That's our big question today. Is it always true that what goes up also comes down? Today on Galileo's Universe. So we know that the reason that the ball returns back to my hand is because of this force of gravity. And gravity is what we're going to take a close look at. But gravity has this amazing ability to attract. You know, I drop a ball, it falls toward the ground. And that's because of gravity. Now, this is a force. And there's actually 4 fundamental forces of nature. But what is a force in the first place? So we're going to start by playing tug of war, and we're going to use tug of war to demonstrate a push or a pull, which is a force. So if I pull, or I push on something, this is nothing more than a force. So just by pulling hard, and then I let go. Oh no. Are you okay? I'm sorry. So gravity is a pull. Gravity doesn't really push too much, but it's one of the 4 fundamental forces of nature, push or pull. All right, well, it turns out that gravity is by far the weakest force of them all. In fact, compared to the other 3 forces, gravity is so weak that if we were as strong as these stronger forces, we would be able to pick up the Earth like it were nothing more than a speck of dust. This is really the big difference between the weakness of gravity, which we all think is very strong, and the other 3 forces. The only reason gravity seems so strong is because it's the entire Earth all together that's acting to pull everything down. All right, well, what are these other 4 forces of nature? Well, the first one is called the strong nuclear force. And with the word nuclear, you can imagine that it works on the nucleus of an atom. Now, if we use a water molecule as an example here, our water molecule is made up of 2 hydrogens and 1 oxygen, the red one in the center. Now, if we zoom in on just one of these, so let's take hydrogen. Hydrogen is the simplest atom. If we zoom in, we'll see inside that there's a single proton and a single neutron. It doesn't take much force to keep those together. But if we go to larger atoms, such as beryllium inside of the nucleus has got 4 protons, which are represented here, and there's also a few neutrons, and neutrons are neutral. Protons are positive. Now, if you've ever taken a couple magnets and you put them together, you squeeze them together, they repel. These positives all are trying to repel each other, but it's the strong nuclear force that's fighting against that and squeezing them together, keeping them in place. All right? So that's our strong force, by far very, very strong. Very, very, very strong. Now, when we break these, by the way, if we split them apart, this is called fission. This is what happens inside of stars. It's also the same kind of thing that happens inside of nuclear power plants, where we're breaking apart. And that energy that's released from the strong nuclear force releases tremendous amounts of energy that powers the stars and also gives us energy inside of power plants. The second force is called the weak force. Now, we have to be careful of this because scientists have called this the weak force, but it's really still very, very strong. All right? And this force gives rise to radioactivity. Now, I got some better demonstrations here to show you. I've got a Geiger counter. Now, a Geiger counter is a way of measuring radioactivity, and you'll hear little clicks. Each time there's a click, this is a radioactive particle that's hitting the inside of our detector and giving off a sound. This is programmed to give off a sound when that happens. So I've got some examples here. Well, one example is a radioactive source And this is a basic one, and this is a beta gamma source. There's 3 different types of radioactivity: alpha, beta, and gamma. Don't really worry about it at this point what the difference is. Just if I bring this close, you'll hear that this is fairly radioactive. The weak force is responsible for this. Also, grandparents might have at home very old plates. These orange plates were actually covered with a radioactive material made out of uranium, and the uranium is what gave it its orange color. And when I bring this nearby, you hear it's going off quite a bit. All right? And then a third one we have here that could save your life one day is inside of a smoke detector. Smoke detectors are made to work using americium-241, and you hear again lots and lots and lots of radioactivity from this, but it could save your life. Most homes have got one of these. All right? So that is the weak force. The next one that's even weaker is the electromagnetic force. And that comes from a combination of magnetism, and I've got 2 very small magnets here, but even though they're small does not mean they're not that they're weak. I'm going to put one on here, and if just get close, you notice how strong it is. In fact, so strong that they're able to attract to each other even from a distance. That's part of the electromagnetic force. And then, of course, electricity. I can use the electricity that's running through the wires from this battery to light up a light bulb. And the light bulb is actually a combination of electricity and magnetism. And this is the electromagnetic force. Of course, light bulbs are also, that are inside of flashlights, also are responsible for that. So we've got the strong force, the weak force, and the electromagnetic force, all very strong, and then there's the gravitational force. So with our bowling ball, we can do a real quick demonstration that shows the strength of this, because if I let go, the entire gravity of the Earth pulls down on the bowling ball, and we see the big effect of gravity. So the real question is, how is it that gravity works? Well, the real answer is scientists don't know. They have some understanding of how they think it might work, and the interesting thing is that all things have gravity. We of course know the Earth has gravity, all right? Because we're standing on the Earth. We're feeling a force. That force is pushing us down, pulling us actually. It's an attractive force, all right? But the reality is that this bowling ball also has gravity, and so does the tennis ball. Everything has gravity. Anything that has mass and is made out of matter also has gravity. Now, of course, we don't feel ourselves all being pulled and attracted to the bowling ball because the bowling ball has so little mass, it also has so little gravity, and gravity is a very, very weak attractive force. So we don't feel it, all right? But there are some interesting things we can explore with the pull of gravity. Well, first of all, if let's say I drop a tennis ball or I drop a bowling ball, which drops faster? Well, let's do a little experiment. All right, we're going to take and we're going to drop a sheet of paper, which obviously is the biggest difference between the bowling ball and the sheet of paper, and we're going to drop this. Now, I want you to predict which one will hit first. All right, so here we go. Ready? 3, 2, 1. Well, obviously, there was a big difference between the two because the piece of paper took a long time to float down. But we have another force working here, and that's air resistance. So we're going to just change this piece of paper. All we're going to do is crumple it up so that the amount of surface area that's hitting the air is dramatically reduced. So now, I'm going to take the bowling ball, and I'm going to take the wad of paper, and I'm going to release them at the same time, and let's watch what happens. Okay, 3, 2, 1. Now you notice that they both fall at almost the same rate, and they hit the ground at about the same time. Now, another effect that we can see here on this is, let's do this. I've got a metal plate here and a piece of paper. Again, I'm going to drop them. Let's watch the attractive force between the two. All right, let me do it this way. Ready? 3, 2, 1. Big difference again, all right? Now, I'm not going to do anything to this other than put it right on top. Let's watch what happens. Because now, this is going to act as a shield for the air resistance that the paper will encounter. 3, 2, 1. Now you notice the paper went right down behind it. It went at the same speed. Gravity pulls on all things at the same rate. Scientists have given it a number, 9.8 meters per second squared. That means each second that something is falling, it is increasing its speed by about 10 meters per second every second. So let's put that in terms that we all understand. 10 meters per second is about 22 miles an hour. So you throw something over the edge of a building, it is going to fall at the end of 1 second at 22 miles an hour. At the end of 2 seconds, it's going to be up to 44. At the end of 3 seconds, it's going to be up to 66 miles an hour. So gravity causes this thing to accelerate as it falls. Now, I've got a dirty little secret to tell you. Come here, zoom in, see? Okay, now here's the deal. Scientists have got a little secret, and they've got a couple rules that they use to describe things. One of them is called a law. Now, we have the law of gravity. A law merely describes how something works. So it basically says that the ball's falling and it speeds up and it speeds up at this rate. This is a law of gravity. And some people will say that a law is a much higher thing than another little word that scientists use called a theory. Well, a theory is actually a more powerful thing. So when we say something is a scientific theory, such as cell theory or also theory of evolution, this means that it's really powerful. Actually, in some ways, it's even more powerful than a law because it explains how something works. It's actually looking at evidence, and it also, we can make predictions, strong predictions. Well, the problem is with gravity is that it's just a law. Again, we don't know how it works. We really don't know what's causing the little tiny atoms and particles and molecules to get attracted to each other and to have the Earth attract us to it and us to the Earth. All right? So that's the little secret. Okay, zoom back out, because I got another demonstration here to show you on this. All right? Now, let's take a look at seeing evidence for gravity. All right, I've got another device here, and this is a little scientific timer. And this timer operates by leaving little dots. Now, the dots that are going to be on this paper that I've threaded through are going to be separated by a period of time. And it turns out that this operates so that it leaves 60 dots per second. That translates to 1/60th of a second between each dot, or about 0.0167 seconds. That's fast, all right? So if something falls, then we can leave a series of dots, and then we're going to take a look at the spacing of the dots and see what that evidence tells us about the existence of gravity. So I'm going to turn this thing on, and I've got a billiard ball attached to it, and we're just going to let it fall, all right? Turning it on, you hear clicking, that's leaving the dots, and now we're going to let it fall. All right, now let's take a close look at the dots on the paper. Now, turns out that the dots that are left here, at first, they're very faint. At first, they are very, very close together. But then over a period of time, when you get up here, they get farther away. So there is a dot here, and then there's a dot here, separated by a few centimeters. Down here at the bottom, they're very close, separated by about 1 centimeter. So because the spacing between the dots is increasing, that tells us that gravity is causing it to accelerate. Now, if gravity were not accelerating us, we actually wouldn't feel this force on the floor. You know, when you stand for a long time, you sort of get tired. But that's only because gravity is always trying to accelerate us downward. It's a force that's pulling us down. If gravity weren't doing that, then actually it would be pretty easy. We would sort of lose this force. Sort of the same way that you only get pushed back in the seat of your car when you speed up. That's an acceleration. Or when you slow down, that's an acceleration. But when you're doing a constant speed, like 55 miles an hour on the highway, you really don't feel this pressure. So gravity is this attractive force. But when we come back, we're going to take a look at a little bit more on the effect of gravity in a gravity well. So I have another little secret. Zoom in, zoom in. Okay, let's take a little talk here, and let's talk about Galileo, because our show is called Galileo's Universe. And we called it Galileo's Universe because it pays homage to Galileo. Now, Galileo was this guy that lived about 300 or 400 years ago, and he was actually the first person to do real science. What was real science? Real science is we collect data, we gather evidence, we then draw conclusions from that. And from that, we can develop theories. And then we can test those theories and start to draw more evidence and more conclusions. Up until Galileo, a bunch of dudes would sit around and talk about things and think about things and come up with things. And sometimes they were right, but most often they were not. No, they were not right. Galileo was the first real scientist. Hence, we call our show Galileo's Universe. All right, so let's take a look at a couple more demonstrations here, and one of them is gravity. Now, one thing that you might see on television shows and in the movies is this idea of a gravity well. Now, a lot of times people think that the gravity well is this physical thing that occurs out in space. Anything that has gravity can be represented to have a gravity well. This is nothing more than sort of a way of thinking about gravity, but it doesn't really exist. All right, you've seen gravity wells. They have like this well. It's sort of like the cone here, upside down traffic cone that we're going to use as our gravity well. Now, this is a real well, of course, but we're going to represent gravity with this. So we're going to pretend like at the bottom of this, there's a star, like the sun. And the deeper this gravity well is, the stronger gravity is. This is just a way of thinking about it. So I'm going to use a little marble, and this comes in close to a gravity source. And as it gets attracted, it starts to get pulled in. And I'm going to then put it down here, and we're going to watch what happens as it gets closer and closer to the gravity well. So I'm going to give it some initial speed, and then let's watch what happens. All right, so you see it starts to spin faster and faster and faster as it gets toward the bottom. And this represents what happens when an object gets captured in an object's gravity well. It essentially goes into orbit. So the Earth is in orbit around the sun, and so the Earth is in the sun's gravity well. It doesn't mean that it's physically in a well like this. We just represented it as this well. The moon is in orbit around the Earth. The moon is captured by the Earth's gravity well. Now, turns out that there are some gravity wells that are so deep that nothing ever escapes. Now, that nothing that ever escapes is light. And light is the fastest thing in the universe. It travels at 3.0 times 10 to the 8th meters per second. That's really, really fast. That means from the Earth to the moon's about 250,000 miles away. Light can get there in a second and a half. Very, very fast. What took days for the Apollo astronauts to get there takes a second and a half for light. But light